In this lesson, we'll discuss the tail risk measures, namely value at risk VaR and expected shortfall or ES or conditional value at risk models. First, we discuss the theoretical underpinnings behind the VaR measure. Then we provide the mathematical formulation behind the same. Then we conclude the discussion on VaR with a few important numerical examples. Next, we provide the shortcomings of VaR that offer the motivation to explore the C-VaR or conditional VaR measure. We introduce the C-VaR measure and its useful properties. Then we provide the mathematical formulation to C-VaR measure. Subsequently, we concretize our understanding of the C-VaR measure with a few simple examples. We close the discussion with summary and concluding remarks. In the series of next few videos, we'll discuss a very important tail risk measure, that is value at risk measure or VaR measure. The measure is often employed in risk management by financial institutions, for example, employed by banks in the portfolio performance and risk management, employed by financial market exchanges for their margin requirements. Consider the distribution of T-period returns. It appears to be a normal bell-shaped curve like this. On the positive side, generally you have positive returns or what we call as gains on the right side, and on the left side you generally have the losses or negative returns. Now let's say we want to make a critical statement about our position that we are X% certain that we'll not lose more than $V in time t. So two important parameters of this VaR measure is time t, the period over which we are examining our data, and our confidence or certainty level at X%. Let's say this X% is our confidence level. Then in that case, if this is a gain distribution, that means on the right side we have gains and on the left side we have losses, which are generally negative returns, then we are looking at 100 minus X percentile value, which means if we want to be X% certain, then we are looking at, on this distribution, 100 minus X percentile. For example, let's say if the value is 95 percentile, X takes the value of 95 percentile, then what we are looking at is 100 minus 95, which is 5 percentile of the distribution, which should be somewhat here, 100 minus X, and this would be generally a loss value, negative return or negative value associated with this. So we'll say that this value V is the loss that we are X% certain, in this case 95% certain that will not lose more than this amount, 95% times in time t. T is the time period that is under consideration, which also means basically this is the area under the curve, which is 95%. So 95% chance is there that will not lose more than this value. And what is this V? This is 100 minus X percentile on this distribution. So we are essentially making a critical statement that we are X% certain that we will not lose more than V in time t, a period of t. It can be daily, weekly, or any time period under consideration. So the variable V here, which is the value that we will not lose, is the t day 100 minus X percentile VaR of the portfolio. I repeat, V here is the VaR on t day 100 minus X percentile VaR of the portfolio, that is 1% VaR of the portfolio. This VaR, variable V, which is the VaR of the portfolio, it is a function of time period which is under consideration, and confidence level X. Often this VaR is also expressed in terms of loss function, which is opposite of gain, sort of negative gain. In the loss function, your gains will be on this side, on the left side, and your losses will be on this side. So if you are talking about loss function and we are associating a 95% confidence, then we are looking at 95% percentile itself. We are looking at this side, right side of cutoff, which is 95% of the area, sort of this area, cumulative area of 95%. And then in that case, VaR is expressed in terms of losses or negative gain, and we say that on the gain for negative gain or loss function, this is 95% VaR. On the negative gain or loss function, 95% VaR. So the cutoff point is 95% VaR, and we make again the same statement that we are 95% certain that we will not lose more than V dollars, which is this cutoff point V dollars in time t. Let's put some values here. For example, when t equal to 5-day horizon, when we are looking at possible losses over 5-day horizon and a confidence level of 97%, so that means you want to be 97% confident, then VaR measure, value at risk measure, is the loss over next 5 days. Either on gains distribution, it is the third percentile value. If you're looking at gains distribution, then this is the third percentile value. That means if it is a gains distribution, here you have gain and here you have losses, then in that case third percentile. Or if you're looking at loss distribution, that means losses on this side and gain on this side, then you're looking at 97 percentile. This side, 97 percentile of distribution of losses. So again, to just repeat that, if you're considering the loss distribution, you have losses on this side and you want to be, so let's say 97% confident, then this cutoff value is 97 percentile. That means the area under the curve, area in this probability distribution, this area is 97, cumulative area is 97 percentile, or essentially this point is, cutoff point is 97. In case you are looking at the gains distribution where gains are on this side, positive returns, and losses on this side, then you are looking for V on the left side. On the left side of distribution, the losses are here at around 100 minus 97, which is 3 percentile. So this cutoff value would be 3 percentile, and both of the values will be same because there is a symmetry in the distribution. So both the values will be same, and whatever value you find V as VaR, you would make a statement that you are 97% certain that over a 5-day horizon, your loss will be not more than V dollars. To summarize, in this video, we discussed and introduced the VaR, value at risk measure. We noted that VaR on a given distribution of returns, gains and losses, it is sort of maximum loss that would occur over a given horizon or a given period, let's say T days, maybe 5 day or a week or month, with a certain confidence level X, that is maybe 95% or 97%. The interpretation changes depending upon whether we are looking at the loss distribution or gains distribution. We said that on a loss distribution, we look at the right side, and if we want to be, let's say, X% certain, then we look at the cutoff point as X percentile, which gives us the cumulative probability here on the left side. And this X percentile becomes the cutoff to estimate the VaR V on the right side. While when we are looking at the gains distribution, where gain side is the right side and loss side is the left side, then if you want to be X% certain, then we look at X 100 minus X percentile on the left side, which is the loss side. So for example, if you're looking at 95% confidence, then you look at the 5% cutoff value on this side, which is the V, or rather it will be negative some kind of loss value, which is your potential losses, maximum potential losses over a given horizon T with a confidence of 95%. In this video, we'll continue our discussion of VaR and we'll provide a more formal mathematical definition of the theoretical concept that we have discussed till now. Recall how we expressed VaR. We said that if you are asked on any given day, let's say we are talking about daily periods, and we say that what is the probability that you can lose more than 10 million. So you may reply by saying in the following manner. You may say that on any given day, if daily is my horizon, I'm looking at daily periods, then with 95% confidence, I cannot lose more than 10 million on my portfolio. Or it can also be expressed in terms of rupee or dollar value, or also the return, negative return amount, which is essentially losses. So I can express my loss, maximum loss for this 95% confidence as some value in rupee or dollar amount as 10 million or something, or negative return of X%. This is also, if you think of it, this is also same way of saying that though there is also a chance of 5% that my losses can exceed. I repeat, there's also a chance, or there's a way of saying that there's a 5% chance that my losses can be more than this amount of 10 million or X%. And therefore, we may express our VaR value in two ways. We can say that when we are looking at gains distribution, then we are looking at left tail for losses. Then we may say that 5% daily VaR is some loss amount like 10 million, or X% negative return, that is losses. Or if you're looking at loss distribution, then you may say that I'm looking at right tail, and then we can say that 95% daily VaR is 10 million, or the amount that I think that I would lose, the maximum amount that I would lose with 95% confidence. Think of a return distribution, rather loss distribution, appearing like this. For now, we'll ignore this C-VaR and the extreme tail. We are talking about VaR only. So we are looking at normal scenarios with some 95 or 99% confidence. In that case, on y-axis, we have frequencies or probability distributions, probability densities rather. And on the x-axis, you would have losses. on the right tail and gains on the left side. You can express losses in rupee dollar amount or also in percentage return terms. But we generally tend to convert them into what we call as standard normal distribution or Z values or Z distribution or Z distribution, which is Z equal to X minus mean upon standard deviation, where X can be, for example, returns or rupee dollar gain losses, mu is mean and sigma standard deviation. So you convert, to make it more easy to interpret, you convert into Z values or standardization. This is called standardization. And that is why when you have Z values or Z values on x-axis, this is called standard normal or some kind of standardized distribution. Now, when we are talking in terms of standardized distribution, let's say you're looking at 95% VaR, because we are talking about loss distribution. So we are saying 95% VaR. That means essentially we are looking for a loss value on this side or corresponding Z value to a loss where the area, the cumulative area on the left side is 95%. Why 95%? Because we want to cover a 95% chance that we are well covered. We want to attach a 95% confidence. So we are looking at the cumulative probability on this side at 95%. Now we are looking at a Z value that gives us this confidence or this cumulative probability on the left side of 95%, or rather alpha equal to 95. Once we have the Z value, we can convert it into the actual rupee dollar loss or loss in the form of return percentage X percentage. But we are defining or providing the formal definition of VaR in these Z terms. So this is nothing but the definition of percentile itself, which is to say that this is the minimum value of Z. This is the minimum value of Z for which the cumulative probability almost exceeds this 95. You can express it as greater than equal to or greater than, which will almost, because it's a continuous distribution, it would not change much. So this is an amount which is greater than equal to alpha, which was 0.95 or 95%. So this is nothing but the definition of percentiles only, and we are looking for a cutoff point Z, which gives us the cumulative value of 0.95 here on the left side of it, which on the loss function becomes our percentile. If we are looking at the gain function, we would have looked for the 5 percentile, but we are looking at loss function, so we look at 95 percentile, and that becomes our VaR value of X. Later we'll convert this Z value into corresponding X loss value in terms of rupee dollar or percentage terms, but this is the formal definition of our VaR measure, that is the minimum value of Z, which has a cumulative probability on the left side equal to that cutoff, which is nothing but the definition of percentile itself. To summarize this video, we provided a more formal mathematical definition of VaR based on previous discussions that we had. Previously we discussed in a more qualitative manner, but now we have provided a more formal mathematical definition, which is same as the definition of percentiles or quantiles. In this video, we'll conclude our discussion about theoretical underpinnings of value at risk or VaR models. We'll also discuss how to compute VaR from empirical dataset. To conclude our VaR discussion, we said there are three important inputs to define VaR or value at risk for a position or portfolio. First, the time period, the daily or weekly time period over which we want to estimate the losses. Second, the level of confidence which leads us to probability values, maybe 95% confidence or 99% confidence. Last, and a very important measure, which is the estimate of loss, which can be in absolute rupee dollar terms or percentage return terms. Now, the missing piece here is how to attach this confidence level to the estimate of loss, and that requires us the distribution of returns or losses, maybe a standard normal distribution, or we can have empirical data. In case if we have standard normal distribution of returns daily or whatever horizon we are interested in, that periodic return distribution we have already seen the mathematical formal definition of VaR to estimate the loss using this standard normal distribution. The percentile definition we have already seen, applying which, if we have the standard normal distribution for daily, weekly, or any kind of periodic returns, we can estimate this loss by modeling the returns through this distribution. But what if we have the empirical data? Then what to do? So let's discuss how to estimate VaR when you have discrete empirical observations, rather than, although more desirable is to have some kind of distributional properties like standard normal distribution, but in the absence of that, how to estimate with the empirical discrete observations. And for a case, for explanatory purposes, I'll use a rather simple case that I have 1001 observations, which includes starting from observation number 0 to 1000. Here it is interesting that I am noting the first observation as 0. You could have also noted it as first, but then the last observation is 1001. You'll see why I'm doing this. Now let's say you are interested in daily horizon. So these are daily return observations. The first thing you can do is you can order them in a decreasing fashion. So the maximum return is, let's say, one observation number 1000, and the lowest return is observation number 0, or 1 to 1001. That also you can pick. In that case, the observation number which is at 990 is sort of a very important point here. Let's say I'm looking at 99% cutoff or 99 percentile value. Then the observation number 990, you can think of the entire set as 1000 periods. So the 99% period will end, will cut off the entire segment into two parts. So this 990th observation will essentially cut into 99% and 1%, two segments. Starting from this maximum value, this 990th value will be the 99 percentile. Now think of this data into segments, and this 990th observation will divide the upper right side into 1 percentile segment, and therefore it represents that cutoff level or that 99% confidence level that we are interested in. That means if I choose this cutoff value, then 99% of the intervals will fall on the left and 1% on the right. This 1% is the extreme sort of observations, and therefore this cutoff point becomes my 99% daily VaR, because it distributes the two or segments the entire horizon into two segments of 99 versus 1%. So this becomes, and obviously because we have started the maximum value here and minimum value here, so this is our loss side where negative returns or negative losses are there. So this cutoff value will become the point at which we can be 99% confident that my maximum loss will be this value. Similarly, you can think of 95%. So then I can use the observation number 950 as a 95% cutoff, because the observation, because the 950th, this 950 observation starting from this 0 to 1000 will distribute this segment into 95% length here and 5% here. So this becomes my 95% cutoff. That means 95% of the observations on the left, and these are the 5% extreme loss sort of observations. So I can say with 95% confidence that this will be my maximum loss. It is customary to have this side. There's nothing theoretically that stops this side also having positive returns, or not exactly losses but lower returns. But generally in a practical sense, you will tend to have negative numbers, negative return numbers here. To summarize this video, we discussed and concluded our understanding and theoretical discussion of VaR. We noted that while it is desirable to apply some kind of distribution like standard normal distribution to model the returns and obtain VaR measures, but also often you have discrete empirical observations, and how to model our returns with these discrete empirical observations and find certain VaR values like 99% VaR and 95% VaR that we saw in this video. In the next two videos, we'll try to reinforce and concretize our understanding of VaR, value at risk, through two simple numerical examples. Let's start with this first example, where a sort of hypothetical gamble is designed that from a loss of 50 million to a gain of 50 million, all outcomes are equally likely over a period of year. So this is a sort of example of a uniform distribution. That means the outcomes are distributed on probability distribution table, where on y-axis we have probability densities, probability PDs, probability densities. On x-axis we have possible outcomes. They start from a value of minus 50 and they end up with the final value of plus 50 million. You can think of mid value or mean value as 0. But the point here is that this height is same for all the outcomes. That means all the outcomes are equally likely. Also, please recall that this is a version of gain distribution, because here on the right side we have gains and left side we have losses. The other way around would have been starting from 50 million gains here and losses here, then this would have been the loss distribution. So now if you are looking at either 1% on the gain distribution, which is on this side, 1 percentile cutoff, or sort of 99 percentile here. To simplify things, on either these graphs, you can think of 1 million intervals of 100 pieces, where for example this is minus 50 to 49 and 49 to 48 and so on, starting here 49 to 50. So you can think of 100 such intervals of $1 million each, or INR 1 million rupees of each. You can construct such 100 intervals. Now if I'm interested in 1% VaR, then means on the gains distribution, either I am looking at this cutoff which is at minus 49 million or 49 million loss, or if I am looking at loss distribution, either I'm looking at this 99 percentile point cutoff, which is nothing but again minus 49 million rupees loss. So either I look at gain side or loss side. If I want to have that 99% confidence, then I'm looking at 1% on the gain side, which is this, or 99% on the loss side, which is this, and both values are same as 49 million loss. Similarly, if we are looking at 95% confidence, then let's start with the gain function. This is minus 50, this is plus 50, and we are looking at 95% confidence. That means on the gain distribution we are looking at 5% cutoff, which is 100 minus 95, which is this 5% cutoff. Now it's too easy to know that this will be 5 intervals of 1 million rupee each, which will end up at what point? 45 million. So this would be the 45 million loss point, or minus 45 million. Similarly, if I'm looking at the loss function, then essentially it would be 50 to minus 50, and in that case also we are looking at on the right side 95% cutoff point, which would again be a loss of 45 million. So because this was a uniform distribution, things were rather simple for us to understand and estimate the cutoff points at 95% and 99% confidence levels. To summarize this video here with a simple example, numerical example, where the approach employed uniform distribution, we saw how to compute VaR for 99% and 95% confidence levels. In this video, we'll discuss a more systematic approach to VaR estimation with the help of probability distributions. Before we start with our numerical example, please recall that when you are making an assumption about probability distributions, you need to connect that distribution, probability distribution, with your return data. For example, take a case in point with normal distribution. Generally, when we are talking about normal distribution, normal probability density distribution, we tend to use standard normal distribution, which are defined by z values. So on x-axis you have z values. So you have to convert, let's say you have a return data in percentage returns or continuously compounded returns, then you have to convert this return data into z values or z distributions. How to do that? You subtract the return from its mean and divide it by standard deviation. It's a pretty simple procedure. That is r, return data, minus its mean mu, which is the average of return, divided by standard deviation sigma. So this is how you get the z values. Now instead of return values on x-axis, you have z values, and as we'll see shortly, it has a lot of beneficial properties. Now let's say you are interested in sort of 99% confidence interval, and assuming that is a regular gain distribution, where on positive side we have, on the right hand side we have positive returns sort of gains, and on left side we have negative returns or losses, then in that case, if you're looking at 99% confidence, then essentially your 1% area will be this. This will be your 1% area where you are interested in. So what you'll do is you'll use the benefit or sort of properties of normal distribution to find this cutoff point. Cutoff point in the sense that right hand side probability, cumulative probability on the RHS is 99%, and therefore this becomes your cutoff value at 1%. Similarly, if you want to find the cutoff value or sort of 95% confidence level, the procedure remains identical. All you need to do is find a point to which right side cumulative probability is 95%, and therefore this left side tail area becomes 5%, which is the cutoff point in z terms you will obtain. Once you have the z value corresponding to this cutoff point, then you can convert the z value into return form and subsequently compute the losses in actual rupee or dollar terms. This was about gains distribution. So now if you're thinking in terms of loss distribution, you have to follow the similar procedure, only that now on the right side you will look at 95% or 99% cutoff depending upon your confidence level. So now let's start with our numerical example. The example is as follows. Abhishek purchased a share of 1000 rupees where continuously compounded daily returns are distributed with a mean of 12.5% per annum. So this 12.5% is per annum. So we need to convert it back to daily level, and a standard deviation also of 50% per annum. So we'll convert this back as well at daily level. The question is how much value at risk or VaR margin needs to be deposited if you want to have a 99% confidence. Also, it is given that there are 250 days of trading in a year and returns are serially correlated. This is very important assumption before modeling or employing any kind of distribution, that returns are serially uncorrelated. Particularly when we are translating volatility across different periods from annual to daily and so on, then this assumption is very important. Now we are supposed to compute the VaR margin for 1 day and 3 day period, and it is given that Z value corresponding to 1% significant level is minus 2.326. The application of this Z value goes like this. So if you recall our previous discussion, this 1% point is corresponding to minus 2.326 here, Z value, and the right side probability would be 99. Similarly, if we were looking at the loss distribution, then on this side Z value corresponding to 99% is positive 2.326. You can employ them either way, either looking at left side or right side. The value is symmetrical, only that here it is negative and on RHS it is positive. So let us start with our numerical. First we'll compute the returns on daily, because our horizon is on daily basis. If you recall, the period was one important input. What period we are looking at, that was one important input in our analysis. So 12.5% is given at annual level. So let's compute it at daily level, and it turns out to be 0.05%, which is we got after dividing by 250. Why did we divide by 250? Because there were 250 trading days in the year. So we divided 12.5% by 250 to get 0.05%. The computation of standard deviation from annual to daily is not as simple. The formula for any periodicity is sigma t is equal to under root t into sigma for one period. So here the period is total 250 days. So I need to divide it in order to compute it for daily. I need to divide it by 250. That is sigma t upon square root t equal to sigma 1. This is what we needed to do. So we have 50% total volatility annual basis. So we divided by total trading days sigma root 250 to get this 3.16%. Now the last missing piece is that Z value, which is given to us minus 2.326. So that means we are looking at the sort of gain distribution. So we are looking at the left side of it, and Z value is minus 2.326. All we need to do is connect this Z value and find a corresponding return value on the normal distribution. Already this Z value gives us that 1% sort of VaR number, or maximum loss with 99% confidence. So how do we compute it? The formula is simple: mean mu d plus Z into sigma d. Mean is 0.05%. Z value is negative at minus 2.326 into sigma, which is 3.16%, which we got here. So our return value is minus 7.3%. Now let's say if your portfolio value, your investment in this portfolio was 1000 rupees, then in that case the losses that you can expect on any given day, the maximum loss with 99% confidence is 73. I'll repeat, this is a very important statement that I'm making from VaR's perspective, that one day VaR with 99% confidence or 1% significance here was 7.3% in return terms, or in value terms, loss of 73 rupees with 99% confidence. This is my maximum possible potential loss over a daily horizon with 99% confidence. Let's see how to work this number for 3 days. So first we'll convert our return to 3-day period by multiplying the daily return with 3. So we get this number. And second, we also need to multiply the daily volatility sigma 1 day, which is 3.16%, with square root 3. So this is nothing but under root t multiplication to one period standard deviation. So now that we have our return and standard deviation values, it's very easy to compute the potential maximum 3-day loss with 99% confidence. It's exactly identical procedure. We have mean, return, plus Z into sigma 3D. Mean we have already computed as 0.05% into 3 minus 2.326 into square root 3 into 3.16%, which works out to slightly higher than minus 7.3 at 12.55%, which is to suggest that if my portfolio is of 1000 rupees, then the maximum 3-day loss, the maximum potential 3-day loss with 99% confidence would be 125 rupees 50 paise. That means 125.5 in loss terms. So to put it in simple terms, what we are saying that your loss value for a 3-day period with 99% confidence is minus 12.55%. in negative return terms or loss value. Or let's say if you are holding 1000 rupees worth of portfolio, then your loss with over a 3-day period, maximum loss over a 3-day period with 99% confidence is 125.5 rupees. To summarize, in this video we saw how to apply a normal distribution to compute value at risk measure in a more systematic manner. In this video, we'll conclude our discussion about value at risk models with its shortcomings and therefore the motivation to study expected shortfall, or what we call as conditional value at risk or C-VaR models. Let us consider the profile of two portfolio managers or fund managers A and B. While up till a certain point, the value remains same. However, portfolio B differs in the sense that it has taken certain position in certain securities, where in the extreme tail may be 5% or extreme tail of 1%, the loss probabilities are extremely high. So we can see extremely large possibilities, but these are hidden. These probabilities are in tail manner. So to a portfolio manager who is specifically focused on the value at risk, that is the 95% scenarios, may not be able to look at these loss measures because he is solely or focused on this region, which is identical for both the positions. But the main difference lies here in this loss, which is an extreme loss, which is not for portfolio A but for portfolio B. The question you may ask, why portfolio B manager would be interested in such a position? Maybe because in this position, on the positive side also, he may have some kind of upside. He may witness some kind of upside on the positive side, and if the positive side were to appear, his bonus would be very high. But his sort of negative side, his performance is judged based on this VaR number, and his performance is not evaluated based on this loss that may happen if extreme scenarios were to take place, because this is hidden as per VaR model. So if he is judged or evaluated on VaR model, he will be penalized only for this value V, not for this extreme risk that he has taken, because this risk appears in the extreme tail and not captured by the VaR. So to somebody who is looking only at a VaR as a measure, both the positions, portfolio A and portfolio B, will appear as of similar risk on the VaR. Like I said, his motivation would be probably there is some, on the positive side, some excess gains that he is expecting because of this extreme risk taking. And this motivates us to look at something called conditional VaR or expected shortfall models that precisely look at what were to happen if indeed some extreme events were to take place. So if this extreme events were to take place, then what would be his losses? That is what we examine in conditional value at risk or C-VaR models, or what we call as expected shortfall models, that are the topic of next set of videos. To summarize this video, we discussed the shortcoming of value at risk models, that is, they are not able to identify if there is some kind of extreme risk position on negative tail, and this motivates us to study what we call as expected shortfall or conditional value at risk models. Starting from this video and in next few videos, we'll introduce and discuss a very important measure of tail risk, that is conditional VaR or expected shortfall. Previously, in the VaR or value at risk measure, we said how bad things can get. But now here we are saying if things do get bad, what is our average expectation or our expected losses? So the VaR method covers all the possibilities with a certain confidence level. If that confidence level were to hold, then what is my estimate of maximum loss? However, there are chances that this position is exposed to those losses that they are beyond confidence level. So if you recall, the area that we ignored in the VaR is the tail region. So whatever we said, we stopped at this cutoff point, which we called as VaR. But here we also look at that tail region. So we are more interested in tail region. That is, if these extreme scenarios were to materialize, what would be our losses? And to cover this kind of exposure, the extreme tail losses, a more advanced version of risk measure, that is C-VaR or conditional VaR or expected shortfall, is proposed. This measure computes expected losses given that or conditional upon the fact that confidence level is breached. In mathematical terms, that means your losses exceed your VaR level. So VaR level tries to compute certain level of maximum losses, this VaR level. If this VaR level were to breach, then what were to happen? If this VaR level was breached, then what were to happen? That is, the scenarios beyond a certain confidence like 99 or 95% have been breached. So in simple terms, essentially with C-VaR or ES, what we are saying, that earlier we had a VaR measure, which was this, which gave us idea of how bad things can get. But if things do materialize, the bad things do materialize, that means this VaR level is breached, and conditional to the fact that our losses are more than this VaR, that means we are in this region, then what is my expectation of losses? How much losses I can expect? Let's put some numbers here. So for conditional VaR, C-VaR or expected shortfall also, we need to compute the VaR measure again, and then only we can proceed with the C-VaR. So let's say we have for x value of 99% confidence for our t days, 10 days period, t equal to 10, VaR is given as 10 million. That means with 99% confidence, we can say that over a 10-day horizon, our maximum loss would be 10 million. So this is the maximum loss with this much confidence in this period. Now, what C-VaR or expected shortfall says is that if my VaR is more than 10 million, assuming that this 10 million is breached, that means my losses are more than 10 million. That means we are beyond this 99% level. So if there was this 99% cutoff, which was my VaR at 10 million, given that this 10 million level is breached and now we are talking in this level, what is my expected level of loss for a 10-day period, given that this loss is greater than 10 million or this 10 million VaR level is breached? So in simple terms, what we are saying that we have already assumed that this level is breached, we are already beyond this redemption level of this much, and we are already dealing with this level, and in that case, what is my expected losses? Now the intuition that I want us to understand is that in this particular case, if this is your risk measure, recall our one of the two portfolios, portfolio A and portfolio B, where we said that with VaR level, there is a motivation to set up this kind of portfolio where there is a extreme possibility in the tail, this extreme tail possibility of loss. With this kind of C-VaR or expected shortfall measure, the tendency of fund managers to set up this kind of position where there is a in the tail there is extreme negative loss possibility, that will be mitigated. So the motivation for this portfolio manager B to set up this extreme position where there is a extreme loss possibility in the tail, which probably may not be identified by the VaR measure but identified by the C-VaR measure. So if the management or holders of this fund are also looking at C-VaR measure, they would easily identify this kind of position, and therefore the motivation, and probably the fund manager would be penalized, and therefore the motivation to set up this kind of position is less. To summarize, in this video we introduced our C-VaR or conditional VaR method, or what we are calling as expected shortfall. We saw how it improves upon the conventional VaR method and how it demotivates the fund managers. It demotivates the fund managers from taking positions that may entail a very sizable risk in extreme tails, which probably would not have been identified by the simple VaR models. In the previous videos, we have discussed the theoretical underpinnings and provided the basic understanding of C-VaR or ES measure. Now, in this video, we'll concretize and reinforce those understandings with mathematical formulation and providing the mathematical underpinnings or a way to measure this conditional VaR or ES measure. So often there are two ways, like VaR, there are two ways employed to compute ES. Either you can use the empirical data, if empirical data is sufficiently rich data is available, but if not, then when you can use some distributional assumption and integrate over the tail region. What it means is that by basic definition, the basic definition of C-VaR is nothing but the fact that if this x is my loss, let's say I'm looking at the loss variable x, given that this loss variable x is greater than the VaR level. So already we are assuming that VaR level is breached. So conditional to the fact that this loss is greater than VaR of x, then what is the expected value of that loss x? For a continuous normal distribution kind of probability distribution, let's say we are looking at the loss distribution. That means this side we have losses and this side we have gains. So let's say this is my VaR level at 1 minus alpha. Probably we are looking at 95% confidence level, which means this is my 95% level, 1 minus alpha, and this is my VaR. So I would like to integrate the loss into probability density, let's call it df. So I would like to integrate this value from this 1 minus alpha, this is the cumulative probability 1 minus alpha for this cutoff point, up till 1. So 1 is the final last point. So 1 minus alpha to 1, I would like to integrate this x df. where we know that this f is a probability density function. In this case, it is a normal distribution. So we sort of integrating over normal distribution from 1 minus alpha to 1. Now, if you recall the cutoff point, the value of x corresponding to this 1 minus alpha is nothing but the var value, and on the right side it goes till infinity. So theoretically it can be infinite level. So integrating this x df from 1 minus alpha to 1 is almost same as integrating x with values from var. So 1 minus alpha has a corresponding value of x as var and 1 has a corresponding value of infinity. So the same can be transferred in terms of x as integrating var to infinity, which has the same interpretation. So essentially what we mean here is that if we are looking at this loss function, this is our cutoff var point, which corresponds to a cumulative, let's say, probability of 1 minus alpha, maybe 95% or 99%. And starting from this point, 1 minus alpha till 1. So the point, the maximum loss point, which theoretically is an infinite value, has a cumulative probability on the left side as equal to 1. So sort of integrating from 1 minus alpha to 1, which is integrating from var value to infinite value. And therefore, the original formula where we said that given that x is greater than var at certain level of significance, maybe 5% or 1%. If it is 5%, then 1 minus alpha is 95%. If it is 1%, then 1 minus alpha is 99%. Depending upon this number, given that x is greater than this var, what is the expected value of x? Which is to suggest that integrate x starting from var. So we integrate at lower limit var up till infinite, the maximum possible. Theoretically infinite, but in real life you may have, based on your empirical data, you may have some expectations of the maximum possible loss. Integrated dfx, where f is the probability density function. So generally we assume normal distribution to describe returns. So this df would be the probability density function for a normal distribution. To summarize this video, here we provided the mathematical intuition and also the formulation of equations to describe the C-VaR or expected shortfall measure. In the previous video, we saw how to approach the problem of C-VaR or ES estimation when probability density distributions are given, sort of continuous probability density distributions are given. In this video, we'll see how to compute conditional VaR or expected shortfall using empirical data. Recall our computation of VaR with the empirical approach. We said that if 1001 observations are given, we can segregate them. Let's say we are looking at 99% VaR, then we can find the 990th position. We will order the data starting from maximum to minimum and we'll find the 990th observation. The idea was that this 990th observation will sort of segregates the entire observations into two length segments. One is having 99% observations, the other is 1% observation. Similarly, for 95%, we will find a value at 950th, and this 950th will segregate 95% and 5% length segments. Now, with the C-VaR or ES, the idea is that this value, this corresponding value of loss is already breached. That means we are already on the right side of it, on the negative loss side. And therefore, the way to approach this problem is to find all the values. Let's say we are looking at 99% expected shortfall or C-VaR. Then the idea is that to pick up all the values that are higher than this 990th position on the right side of it, all the values that are on the right side, and take the average of them. That average would be the expected shortfall or expected value of loss given that 99% VaR is breached. Similarly, think of 95% VaR. So this is the 95% cutoff. Then you look at all the values on the right side of it. Because we have ranked them from max to minimum, all the values on the right side of this 950th would be part of those 5% sort of extreme loss observations. That is scenario where maximum loss is materialized. And therefore, once you put this cutoff of 950 observation as the VaR value, as a cutoff, minimum cutoff, and take all the values that are a higher loss in terms of magnitude, they are higher, that means indicating loss on this side. You take the average of all those x1 plus x2 plus and so on and take their average. If there are no observations, this will be your expected shortfall or average loss given that extreme scenario of 5 or 1% were to materialize. Now let's generalize this understanding. Suppose in a given data, you have been given probability mass function. That means, let's say there are n observations in the tail. In the empirical data, n tail observations are already given to you. And for those n tail observations, the loss observations are x1, x2, x3, x4 up to xn. These are the losses, possible scenarios, losses in possible scenarios in the tail region, negative losses, and the corresponding probabilities as P1, P2, P3 and up till P1. So in that case, when the probabilities are also given as a probability mass function rather, so the probabilities are given and the values are also given, then your conditional VaR or ES measure is simply nothing but the expected value like this, Pi into Xi, summation I equal to 1 to n, which is nothing but this one, which is Q1 X1, Q2 X2, Q3 X3 and so on. Now here this Q1 is different from P1. How? Please note, once you have decided that your VaR level has breached, once you have decided that your VaR level has breached, then only these are the possible scenarios. So for example, in the actual universe of population, let's say this P1 was 5% in the original scenario. But now in the revised scenario, conditional, we are looking at conditional probabilities, conditional that these are the only possible events. So there may be some other events which are on the left tail, which are on this side as well, but that area is now negated. So we are only looking at these possibilities. So what it means is that now we have to look at the conditional probability Q1. That conditional probability is P1 upon summation of P1 to n. Why we are doing this? Because we already know that this region is breached. So these possibilities are ignored and only these are the remaining possibilities there. Therefore, their summation has to be 1. But in original scheme of things, this was not 1. Probably this is 5% or 10% or 1% depending upon our criteria for VaR. And therefore, if this is the case, then in order to standardize or sort of obtain the conditional probability Qi, we compute Qi as Pi upon summation I equal to 1 to n Pi. Now how it is done, we'll see with the help of a numerical example in the next set of videos. To summarize, in this video we saw how to compute C-VaR or expected shortfall from a given set of discrete probabilities or probability mass function if empirical data is employed. In the next two videos, we'll try to concretize our understanding of C-VaR and ES with the help of two simple numerical examples. Let us go through this example. Here it is given that 97.5% VaR is 1 million, 98% VaR is 1 million, and then a 2% chance that loss will be 10 million. And we are supposed to compute C-VaR or expected shortfall at 97.5% confidence. To simplify this problem, because these observations are discrete, we'll assume some kind of uniform distribution in the tail. That means at 97.5% VaR, it is given to us that this is 1 million level. We'll assume it to continue till 98, and beyond 98 it is given that there is a 2% probability that loss can be 10 million. So there are two particular discrete regions available to us for A and B, and it is given while computing C-VaR, we assume that this 97.5% is breached and the only two possibilities are A and B. So the corresponding matching probability of 0.5% here and 2% here needs to be standardized to 1. That means now probability of A plus probability of B has to be 1, conditional, because we are dealing with a conditional event, conditional to that VaR is breached, and therefore we are in this region only. How to achieve this? So the idea here is to make this summation as 1, and therefore we need to standardize these probabilities on a scale of PA plus PB, because now this new PA plus PB is supposed to be 1. We'll standardize the probability of 0.5 by dividing it with PA plus PB, which is 2.5 originally, and we'll standardize the other probability, which is 2%, also by standardizing it with 2.5. So now their summation P of A plus P of this becomes 1. So in that case, our new expected loss would be PA, which is 0.5 upon 2.5 into 1 million plus 2 upon 2.5 into 10 million, which is our expected loss, which is equal to 8.2. What is this 8.2 million? This 8.2 is our expected loss given that our VaR of 97.5% is breached. That means given that this level were to breach at 1 million, what is the possible scenario, and that value is 8.2 million is our expectation of loss. In this video, we'll conclude our understanding of conditional VaR or expected shortfall with the help of simple numerical example. Let's see how this numerical example works out. So we have been given that a portfolio position has a 95% VaR at a 1 million level, rupees 1 million. Then there is a 3% probability that a loss of 2 million may happen. Another 1% probability that a loss of 5 million may happen. 0.75% probability that a loss of 10 million, and a 0.25% probability that a loss of 2 million may occur. Now we are supposed to compute 95% ES, expected shortfall, or C-VaR, which means it is given to us that what were to happen, what is the expected shortfall or expected loss if this 95% VaR of 1 million is breached. Essentially what they are saying is, let me help you visualize this. What they are saying that given this 97.5% VaR is breached, this level is breached, what were to happen next? Now it is given that, let me plot a level of 2 million here with a probability of 3%. So this is 95%, sorry. So this is 3%. That means 95 to 98, there is a 2 million loss. We are assuming a uniform kind of distribution because these are discrete observations. Next, from 98 to 99, there is, let me plot a slightly less thick bar. 98 to 99, 1% probability. This is 1%. Previously it was 3%, so now it is 1%. And the height of this is 5 million. It is given to us as 5 million. Next, another 0.75%, and I'll draw a rather thin bar to indicate that this is 0.75%. In this region, first is A, this is B, this is C, and the height is 10 million. Another very thin bar with a very remote possibility of 0.25, the region D, which has an area of 0.25, 20 million. So these are the four regions. The interesting thing here is that in the previous case, if I sum up all the probabilities corresponding to event A, which is this A, this is B, this is C, 0.75, and this is D. If I sum this up, PA to PB plus PC plus PD, it would add up to 5%. But now the world has changed. It is given to us that this 95% level has breached, and these 5% are the only four possibilities with us. That means conditional to the fact that this 95% level VaR has breached, these probabilities are the only probabilities, and therefore they should sum up to 1. That means probability of A given that VaR has breached plus probability of B given that VaR has breached plus probability of C given VaR has breached plus probability of D given that VaR has breached should be equal to 1, which means we need to standardize these probabilities conditional to this fact that this VaR has breached. How to do this? Let's see that. So in order to standardize these probabilities, all I need to do is I need to divide them by their summation. That means summation is 5%. So let's say 3%, I divide it by 5%. So I get probability of A conditional to VaR breached. Similarly, I divide 1 by 5, 0.25 by 5, and so on to get all the conditional probability given that VaR has breached. Now that I have revised probability, that is PA dash, PB dash, that are conditional to the fact that the VaR has breached, I can compute the expected shortfall with the same method of expectations, that is 3 by 5 into 2 plus 1. This is PA into RA plus PB into RB plus PC, rather PA dash, PB dash, PC dash into RC plus PD dash into RD, which is nothing but an expression like PI dash. Dash I am putting for the fact that conditional to this fact that VaR has breached into Ri, where I equal to 1 to 4. There are 4 possible events, and we get expected value of 4.7 million. Let us see how to interpret this 4.7 million to conclude and summarize this video. This 4.7 million is my expected or sort of average loss. What kind of average? Probability weighted average loss, given that VaR is breached, and these are the only 4 possibilities. The extreme tail, these extreme tails are the only 4 possibilities available to me, and this VaR has been breached. Given that this VaR has been breached, these are the only 4 possibilities, and their expected value, given these probabilities 3%, 1%, and so on, this is that expected value of 4.7 million. Conventional risk models such as ArcGauge do not provide sufficient emphasis on the negative tail of the return distribution. This inefficiency with the conventional risk models is overcome with tail risk measures such as value at risk VaR and conditional value at risk C-VaR measures. To begin with value at risk models, these models estimate the maximum loss value expected over a given horizon t with a certain confidence X%. While this method tells you how bad things can get, but in case things do get bad, what may happen to our investment portfolio is not known. Fund managers may set up positions with a lower maximum loss value with a certain confidence level. However, these positions may carry extreme tail losses outside the confidence band. Such inefficiency in the portfolio position design will not be identified by the VaR models. To account for this inefficiency of the VaR model, we go to conditional VaR or expected shortfall models. These models examine those losses that exceed VaR, or to put it another way, what is the expected loss given the losses exceed VaR.